love problems like this because they are barely calculus. So these are the ones that, like, once they make sense, you will really love getting these problems. Okay, I promise. You'll love getting these once they make sense. All right, so here's what I'm going to write. I'm going to say g of something equals something. And I'm going to say g inverse of something equals something. Okay? G of something equals something. G inverse of something equals something. I'm going to say g prime of something equals something, right? That's our slope. And then g inverse prime of something equals something, okay? And there's all these little relationships that go on here that have to do with just trading x and y, okay? So the only information they told us, the only thing they said is that you're finding g inverse of x at x equals 2. And from that, you have a domino effect to find everything else using the chart. Now, we don't have to use this. This is just the rest of the FRQ because this is an FRQ problem from 2007. And that's for the other parts. We're only doing part A. So x equals 2 for g inverse, okay? So g inverse of x equals 2, g inverse prime at x equals 2. All right, so if it's the x coordinate of the inverse, what was it for the original function? The y coordinate. Okay, now the table does not give us the inverse. The table gives us the function. So look at the table, look for a y coordinate of 2. Not in the derivative, but in the actual g. That's an x coordinate of 1, so it's right here. That's an x coordinate of 1. Okay, so if I plug 1 in, I get 2. That means for the inverse, if I plug 2 in, I get 1. Okay, so that wasn't too bad. All right, now if it's g of 1 equals 2, then g prime of 1 equals 5. Okay. All right, so what we have here is that xy becomes yx, right? That's what we know about inverses. Xy becomes yx, okay? And with our slopes, change in y over change in x becomes what? Change in x over change in y. So if this is 5 over 1, what's this going to be? 1 over 5. Okay? Now they're saying write your tangent line for g inverse. Write your tangent line for g inverse. So we have y minus a y coordinate equals a slope times x minus an x coordinate. And we're doing it for g inverse. So we don't even need this. This helped us, but we don't need it. There we go. Do you see how those could become favorite problems? But it takes a minute. It takes a minute for them to become favorites.
Whenever they say, like, the x equals 2 at the end, that's not referring to the whole problem and where you would start your g of, like your regular g of.
It's the inverse. X equals 2 means y of the original equals 2. So they said, find the line tangent to the graph of y equals g inverse of x at x equals 2. So this is what they're talking about. G inverse of x at x equals 2. This is the x. All right. Any questions on that one?
Where does the 1 come from? The 1.
So we said if the y coordinate is 2, the x coordinate that corresponds to that was 1. They plugged in 1 to get 2. So we started off with 2. Y coordinate of 2 gives us an x coordinate of 1. Then we kept using the table. We said, okay, well, if 1 is our input, then g prime of 1 is 5. Then, to get our inverse derivative, We just take rise over run, and we flip it, run over rise. Uh-huh. Because it's not perpendicular. So perpendicular is negative reciprocal. This is just switching x's and y's. So not negative reciprocal, it's just plain old reciprocal. Any other questions? Okay, well, let's go ahead and look at the assignment for today. So you guys have had a chance to look at it already while I was sitting on hold. I don't know about you, but I need my yellow sheet. So the ones that you're like, Ms. Rice, how do you need a yellow sheet? You've taught this for 4 years. Here's the answer. The ln's and the e's are the most common. The logs are not as common. The ones that have a base that is not e are not as common. So you're going to get real familiar with ln. You're going to get real familiar with e. You're probably going to always have to go back to your answer or to your yellow sheet for everything else. Does that make sense? So when you do today, really get good at the e's, which is nice, right? Because what's the derivative of e to the x? E to the x. So we don't forget that. And then what's the derivative of ln? 1 over x, okay? So those are the ones we're going to focus on, and then the other ones that were a little bit harder anyway, those are the ones that are not nearly as common, okay? All right, what problem should we do? We can do, okay, let's do 9 first because it's on this page, and then yes, we can do 13. All right, what do you notice automatically about 9? Product rule, we got an x in the front. So since that x in the front is not a number, it's not a coefficient, it is a product rule. Okay, so I'm going to say, do you guys want to use y prime or do you want to use dy dx? Y prime. Okay. How do we start the product rule? First, there we go, focus. First times derivative of the second, so we're going to do 1 over, keep the inside the same, times the derivative of the inside, which is cos. Okay, plus the second times the derivative of the first, okay, minus what is the derivative of these again? Four to the x ln 4, yeah, okay. 4 to the x ln 4. Cool. And at this point, we need to clean it up just a smidge, just a very little bit. What is this? Cotangent. So we have x cotangent x plus Yeah, and I think, so ln 4 is a number, which makes it kind of like a coefficient, and I think the reason they stick it on the end instead of in the front is because ln 4 times 4 to the x is a little bit strange, or it just is not comfortable to, something funky about it. It feels off somehow, so it's not wrong. You can write it, but it just feels a little bit off. All right, there we go. So it's not, so what you're doing is you're just saying minus. It's kind of like this is a -1 as a coefficient, and whenever we have coefficients, we just let them hang out in the front. And so it doesn't have to be, it's not like a base of -4. It would be a base of -4 if you had -4 to the x, but we don't have that. We just have minus and then 4 to the x. So we're thinking of the negative as just hanging out in the front, and then all the rest of the stuff happens. Does that make sense? Okay. All right. Before we go on to number 13, anything else need to happen on the front page? No? Is number 8 a product rule? No, why not? e to the pi is a coefficient, not something that needs to be taken the derivative of. I mean, you can use the product rule, but it doesn't need the product rule because e to the pi is a coefficient.
Take the derivative of pi equals 0.
Yeah. So it works out the same regardless, yeah. All right. So we are saying that the first page is good. Actually, I think, if I remember correctly, I think number 7 does something funky.
Yeah, I was gonna say.
We should do the wrong binder. I believe number 7 does something with properties of logs. Yeah, so that's the thing that you do have to watch out with this, is that properties of logs does come back to bite us. And some students will think like, oh, I must not have done this problem correctly because my answer is not in the multiple choice. And it's not that you did it wrong, it's that they took the answer, they did properties of logs. And so your answer looks different, and you have it, you just didn't do property of logs to condense it, and they did. Does that make sense? Okay, we're going to do number 7 together, because number 7 uses one of the log properties. Cheat sheet? No. All right. So what type of rule does number 7 use? It uses a product rule. Okay, so let's go ahead and do number 7 with the product rule. So do you guys want to do dy dx or y prime? Y prime. So we got y prime is. I'm gonna back way over here, give myself more space. Y prime is, okay, first times derivative of the second, which is, okay, plus times, okay. So as we are cleaning this up, we have ln x over ln 10, right? Ln x, we still have the x on bottom, x ln 10. Oh, ln 10. That was a typo, sorry. And this has what is called the change of base formula, which a lot of us, if you learned it, it would have been in pre-cal. I did not teach it in Math 3. Did you learn it in pre-cal at all? Does that sound familiar at all? Some teachers stopped teaching it once the calculators got better. They used to have to teach this because if you had, based on the calculators, before they started letting you plug a base into a calculator, we had to teach students how to do this because this is how you could plug logs into a calculator. So the way that you do the change of base is that log x over log 10 is actually log base 10 of x. It's the change of base formula. So this is ln x over ln 10. Oops, I don't know why I keep writing that. It's called the change of base formula. And since 10 is the common log, they would just call that log x. Since base 10 is the common log, they would just call that log x. Mm-hmm. So if it was ln 3 over ln 2, you could say that's log base 2 of 3. It was, back in the day, it was how you would plug a log into a calculator if your calculator school. So I'll show you. So if you wanted to type in log base 2 of 3 and you did not have the ability to type it like this, you would type in ln 3 divided by ln 2 and get the same answer. Or you could type log 3 divided by log 2 and get the same answer. It's the change of base formula. So we used to teach kids this all the time because the calculators before the new operating system did not have the ability to do that little base. None of the calculators did it, so we always had to do this change of base thing every single time, and we used to always teach it. Then once the calculators started letting you plug this in, I think a lot of teachers stopped teaching it because we didn't have to do it anymore, forgetting that in calculus maybe the change of base formula would be good to know. So I will say though, I haven't seen the change of base formula show up very often on the actual, this is the only thing, I've never seen it show up on an AP question. But I have seen properties of logs with the expanding and condensing. I've never seen this though, but I did want to address it because it shows up on this assignment because some calculus teacher put it on this assignment. This is not something I wrote. I did steal it from another teacher online. Just letting you know. That's what happens when you, yeah. That's why there's no Bitmoji on it. I mean, maybe I'll put one eventually and just claim it as my own because plagiarism is fun. But all right, so we have y prime equals, so that's what that means is since this is log base 10 of x, we're really going to call that log x. Since it's like a whole number, it's kind of like it's over 1. So what we really have is we have log x over x plus log x over x. Do you see how I did that? Because it was over x right here. There's a leftover x after I simplified it. And so I have the same thing. So what do I have? 2 of them. Yep. See what I mean about like you would get this answer and think you were wrong, but you're not. You're totally right. It's just a property that is a little bit old school because we don't really teach it anymore. We think we don't need to. Yeah. Although I will say, honestly, I've never seen it except for on this assignment, this one problem. But I did want to address it for that reason. Yeah. FRQ, this answer is fine. FRQ, that answer is fine. And again, I have not seen it on a multiple choice problem. Okay. All right. So that one was the funky one on the front page. Okay, so we wanted to do 13. 13 is a very good one to do. Let's do, yeah, 13, let's definitely do that one. All right, 13. dy dx this time? No, y prime. Reagan was game though. She said, sure. Yeah. Just thought maybe dy dx wanted to get some action, but apparently not. All right, so quotient rule, what do we do? Okay, low, d high. So what's the derivative of the top? Get 1 over x ln 3. Okay, low d high minus high d low. What's the derivative of the bottom? E to the 3x times 3. Okay, divided by the bottom squared. Okay. How do you guys think we could clean this up a little bit? Uh-huh. I'm going to leave this as e to the 3x squared because we have so many e to the 3x's. And I don't want to see it as e to the 6x and have a hard time in the future simplifying. Okay. What can we do to make it not a complex fraction anymore? Yeah, so a little bit easier than finding a common denominator is just multiplying by the x ln 3 on the top, multiplying by x ln 3 on the bottom. It looks worse than it is, right? Remember, these always look worse than they are. So what do we get for the first term? Okay.
What if we switch because we're distributing the ln x to, oh, never mind.
Do you guys want to stick the x ln 3 on the end, or do you want to stick it, where do you want to stick that? At the very end. Log base 3 of x times x ln 3. I'm going to put that times in there so that it doesn't look like x squared. It just feels weird to not have a dot there. Actually, you know what? So this x ln 3, the x probably would have gone up with this 3, to be honest. We can clean that up in a second. Okay. So on the next move, we're going to take this x and we're going to stick it with that 3, okay? That's going to be our next move, just because that's probably where it would have been. All right. What do you guys see that can be simplified a little bit? The GCF of e to the 3x. Does everyone see that? On the top, we have that GCF, and we can pull it out of the top, and then we can reduce it with the bottom. You see that? Okay. So on this step, if you guys are okay with it, I'm going to take the x and move it to the 3. So I'm going to say 3x log base 3 of x ln 3. Are you guys okay with that? Yeah. Oh, ln 3. X ln 3. Yes. I missed it putting it on the bottom. Thank you. I read your mind. We noticed it at the same time. I had missed putting it on the bottom. Yeah. So if you missed it, I took this x and I stuck it with the 3 because it normally would have moved to the 3. That's just me being nitpicky, I guess. These x's felt wrong to have next to each other. I was uncomfortable. Okay. And then what can we do? Yeah, we can actually do the canceling. Okay. Yeah, that's fine. I'm gonna write it out. I think the x probably would go in front of the e. Does it matter? No. But you always want it to look nice. It's different than my answer key. It's funny. I mean, the answer is the same, but the order is different. Okay. All right, how are your brains feeling? Brains are okay? Okay. I'm gonna let you guys work. Sound good? Before the end of the period, we have to do a little bit of notes. So in about 20 minutes, about 15 minutes, 15 to 20 minutes, we're gonna do some notes to do another type of exponential problem. Okay, but I want you guys to get some practice in first. Sound good? Yes.
Why does 15 of a star?
Because you're gonna use properties of. So 15 has a star. Use properties of logs before you get started. Before you start. Yes. Properties of logs before you start. Or, honestly, if you used it after, I'm assuming you would still get I think you could still get the same answer otherwise, but the process is easier if you use properties of logs before you get started.
So that means there's log x, log
ln 11, and then what should you do with the exponent? Move it to the front.
So it's x ln 11.
X times ln 11. Yep. Okay. So here we're going to do y equals x to the x. Y equals x to the x. Do you guys see how this doesn't fit? It's because the base is not a number, so it's not acting appropriately. It's not quite like x to a number. It's not quite like a polynomial, so we can't do it. We can't do it where we take the exponent, bring it to the front, drop it, drop the exponent by 1. We can't do that rule. We also can't do the rule where we say like, oh, it's got a base of a to the x power. So we can't use our normal rules here, okay? So we have to rewrite the problem using properties of logs and do implicit differentiation, okay? So what we're going to do here, and this is funky, but we're going to do it, we're going to ln both sides. You can log both sides, but we're going to ln both sides because the derivative of ln is easier than the derivative of log, right? You've looked at that already, it's easier, and we are lazy, okay? So we're going to do the derivative of ln because it's easier. So I'm going to write ln y equals ln x to the x, okay? So anytime you have one like this, and it could be x to the x, it could be sine of x to the x, it could be tan of x to the x, it could be x to the sine. Anytime you have something where you have an exponential problem that doesn't fit, you're going to use this idea, okay? This is one, again, that shows up on the problem set over and over and over again, and if you don't watch out for it, you're going to forget how to do it, okay? So definitely really good example of this on your cheat sheet. All right, now this is where we use the property of logs. We're going to take this exponent, we're going to move it to the front. So we're going to have ln y equals x times ln x. Now y is in like the middle of the problem, right? So we're going to use implicit differentiation. We're going to take the derivative on each side, okay? So what is the derivative of the left side? 1 over y, and then what? Times dy dx, because we had to take the derivative of a y. 1 over y dy dx. When we do the derivative of the right side, we have a product happening. So we have a product rule. So what do we do? Plus, plus, okay. So we have 1 over y dy dx equals, okay. And dy dx is our goal, because that represents our derivative, right? That's our goal. So how could I get rid of the 1 over y? Just multiply by y. Multiply y to the other side. Now, somebody tell me, what was y? It was x to the x. So dy dx is x to the x times 1 plus ln x. That's the answer. You can distribute. Don't need to. So, a little bit funky. Kind of like an outside of the box way to do it. Because you're like, oh, there's no rule there. So anytime we need to get to an exponent that's a variable, we use logs. Okay. Let's do another one just to make sure that we can handle this. So we're going to do y equals sine x to the x. All right, so what should we do? Fill in both sides. Take the exponent, move it to the front. We took the derivative of each side.
Oh, and that's just
So at this point, we have not actually done anything, we've just rewritten stuff. So the equation is still equivalent. We've just done the same thing to both sides. So now we're going to start taking our derivative. And what's the derivative of the left side? And on the right side, we have a product rule. So we have the first times plus the second times the derivative of the first. Okay. Wait, what's cos over sine? Cotangent. So x cotangent x plus ln of sine x. Okay. Multiply your y over. Yep. And then we can take the y out and replace it. Ta-da! So I have a worksheet with these, but it only has 4 of them. Okay, they're very repetitive, so they're exactly the same each time. The issue then becomes recognizing them. It's not that you won't know how to do them, it's recognizing them and remembering this process, okay? So make sure that you do have a good example on your cheat sheet, either one of these or pick one of the ones on the worksheet I'm about to give you, okay? All right, let me hand these out.